Hello, can you hear me?
Yes, I can hear you.
Hey, so hi, welcome to your practice interview. We have 1 hour for the interview, and we'll do the mock in about 45 minutes, and then we can go over feedback towards the end. Before we get started, maybe you can briefly introduce yourself and mention which company you're doing for and when is your next interview.
My name is Franklin. I'm a data science major at Wilkes University, uh, and with a minor in statistics so far. And so I have a specific interest in computer vision. Um, there's a little intro.
All right. And why are you doing this mock interview? Like, do you have some interview scheduled or?
So I'm actually in a program called AI for All, and they introduced to us this platform. So this is actually my first time doing an interview on this website. Um, I'm not
Mm-hmm.
sure if you've heard of AI for All.
Yeah, I did a bunch of interviews from that program. Yeah.
Yeah,
So,
so this is my first.
all right,
Um,
great. And then what would you say your level of ML knowledge is so far? Like, have you done any courses in college, apart from the AI for all, of course?
so mainly it's been self-learning. I haven't completed any ML courses in college, so it's completely up to just some of the books I read and some personal projects. So I have like a brief, high-level understanding of kind of the fundamental machine learning algorithms.
All right, cool. If you're ready, then we can start the interview. We'll just use the coder pad. Feel free to type anything you want here. And I find it good to type a bit of context about your answers as you're answering them.
Hmm.
But you don't have to do that if you're not comfortable. Just it's there for you to use as you would like. All right. Let's start with the basics. So, do you know the difference between supervised and unsupervised learning?
Yes.
Yeah. What's the difference?
Do you want me to type it out, or you want me just to say it out loud, or?
You can say it out loud. If you want to type anything, feel free to do that as well.
So, all right. So with a supervised data set, um, we're going to provide the model with labels, a target, so they
Mhm.
know how to tune the parameters to achieve the target. Um, and with unsupervised algorithms, they don't necessarily know what the right answer is. There's no labels, so they're just trying to figure out specific patterns and present that instead.
All right.
So an example of an unsupervised algorithm would be k-means clustering. Um,
Okay. How does k-means clustering work?
K-means clustering starts by placing a centroid, basically a dot, into this data space filled with data points, and it calculates the average distance between each point to the cluster. And there's the amount of the amount of centroids you can place is you can choose to do that. So you could ask to place like two clusters or three clusters, and so you calculate these distances to the clusters, and you measure. Sorry, I'm going a little too fast. Let me slow down a bit. Um, you place the clusters, and you figure out how much you need to move the cluster to reduce the average distance between the points in the nearest cluster. And you keep on doing that until the clusters don't move as much anymore. Um,
Mm-hmm.
Once they stop moving, essentially you place your clusters optimally in the data space cloud. Um, yeah.
All right. So, do you know what's the distance? Can you write the formula for the distance that you minimize?
Yeah, so I believe that we can just use a Euclidean distance formula. Um,
Mm-hmm.
and we want to find the average distance of all the nearby clusters. Um, So we can use Euclidean distance here. I'm gonna write it E uppercase for E, square roots. So now these points can have multiple dimensions. So um, I'll just say to write the formula. Um, I'll just say like x sub I, uh, x sub j, x sub k, but there could be multiple dimensions with when we're measuring the distance.
Mm-hmm.
So for the first point, our centroid here is going to be x sub I, um, oops, sorry, uh, squared, sorry, plus x sub j squared plus x sub k squared. Okay, that'll be like the first dimension of uh, that'd be the dimensions of the centroid. So this is the center. I could probably name these a little better. So I'm gonna call it like centroid, or I'll call it C underscore to abbreviate to mean the centroid's points. This is a single point in the space. So here are the coordinates to the centroid, and then we're going to add to the centroid the neighbor of a nearby point. So we can call this n for neighbor, x sub I squared.
I'm sure that's right because what's the distance between 2 points in the space? If you have n-dimensional points, um, let's say x1 to xn is 1 point, and the other point is y1 to yn. What's the distance between these 2 points?
Also, you will find to get the distance, you want to find the difference between each dimension, right?
Right, and then square that, and then square root, right?
Oh, so I see what I did here. I made a little error. So it's actually going to be minus the
Yeah.
the neighbor's point as well. We're going to square that.
And it's also going to be whole squared. So it's not x1 minus x, it's not x1 square minus y1 square, right? Instead, it's like this is wrong. Instead, it's x1 minus y1 whole squared.
Oh, okay. I see.
So on each dimension, you calculate the differences. And the reason you do the squaring before you add and then you do the square root is just an easy way to handle like negatives.
Yeah.
Yeah,
I Okay.
we are
So
interested in the absolute difference, right? So, all right.
yeah. So that would
Okay, let's go. Do you know any supervised learning algorithms?
so you have decision trees.
Okay, let's start there. What are decision trees?
So yeah, decision trees are supervised learning algorithm that the way you can describe it as you make a decision at each step within the tree. And the way the decision is calculated is so you ask a question to the data set. This can be like, okay, is this predictor value greater than or equal to 0. 0.5 or something like that? You ask a question, and then you branch off to the left if it's false, and you branch off to the right if it's true. And essentially, you recursively go down the tree asking more and more questions. Um, and when you reach the end of the tree, your goal is you get to separate the data as much as you can um, using a measure called Gini impurity. Uh,
All right. Um, so yeah, that brings us to like how do you actually train the decision tree, right?
yeah.
So you want to decrease the Gini impurity. Do you know the formula for that?
Um, hmm.
Or okay, maybe the concept behind like that. What does that measure?
So it measures. So if to explain a bit easier, if we're talking in classification context, right? Gini
Mm-hmm.
impurity is how imbalanced that subset of data is, right? So if your goal is to minimize that as much as you can, you want it to reach to zero. Zero means that your subset data is all one belongs to all one class, right? So if you have so the higher number your Gini impurity is, the more imbalanced it is. So you have like a mix of classes in your subset of data.
Right, right, right. So you want to find the splits in the data set that sort of are able to split the data set into, let's say, it's binary classification. So you want all the trues on one side, all the falses on the other side. And
Hmm.
if like a split is, giving you half trues and half falses, it's a bad split. If it's able to split, all the trues on one side, all the falses on the other, then it's a good split, right?
Yes.
And that's how you measure the quality of a split is using this Gini impurity function.
Hmm.
All right. So how would you actually train a decision tree? Like, would you just find different splits and keep doing that till you find the best split?
Yeah. So what I would do is I would let me think here. I would go through each feature, right? I would iterate through each feature, find the best split, find the feature that gives you the best split, and then I would recursively do that again, keep on finding the best split for the features that are left over, um, until the user specify parameters for how deep you want the tree to go, um, and for that specific feature, when I mean by find the best split, I mean find the lowest Gini impurity of the feature. And you have a whole selection of features. You want to choose the feature that gives you the lowest amount of Gini impurity right off the bat, and then you will recursively do that. Um, you will split off the branches, doing the best you can, like finding the best Gini impurity each step of the way.
Got it. A common parameter used in decision trees is max depth. Why is that a good parameter?
What do you say, max depth?
Yeah.
Yeah. So this kind of goes around the concept of what's the word? Overfitting, right?
Yeah.
Underfitting and overfitting. That's exactly why the parameters is used for. So if you have a high depth, that means that your tree is going to be large. It's going to be very large. It's going to have a lot of levels and a lot of leaf nodes. That means that um, your tree will be likely to overfit your data. Um,
Why?
so if you want to regulate that, if you want to reduce the depth so that it's not as it isn't learn the data too much, right? Um, you can reduce the depth to lower levels, like instead of 10, you can go to like 3, um, and it won't fit as closely to the data. It'll be more generalizable if you lower the parameter or the hyperparameter.
I think that makes sense, but can you explain a bit more why a higher depth would fit the data more? What do you exactly mean by that?
Yeah. So what happens when you increase the depth, right? Um, it, at a certain point, when you keep increasing the depth, it's eventually going to capture spurious relationships or specific patterns in the data that you don't want to capture, that
Mhm.
don't really help you in terms of predicting the target. So you have to find a good balance between the max depth.
Yeah, yeah.
Um,
I get that, but like, why? That's what I'm trying to like just double click on. Why would it learn patterns that you don't want it to learn, and what are those patterns? Like,
yeah. So eventually it starts straying away off like the main relationship in the data, and it starts picking up on noise, which is
hmm
like outside that relationship. So when you increase that depth by too much, then it starts venturing in the noise of the data, and that noise is not a large contributor to predicting the target. And so then you start learning these spurious relationships that don't really help you in the end.
but yeah, that's the right answer, right? It learns the noise,
Yeah.
memorizes the noise, right? And then that hurts generalizability. So, how do you know if a model is overfitting?
If it isn't overfitting,
Yeah, just generally outside like decision trees for any machine learning model, is there a way that you would know that it's overfitting?
yeah. So one of the main ways, when you have your data set, you often split it into partitions, right? You have a training
Mm-hmm.
set, you have a validation set, and you have a testing set. So signs of overfitting in a model are usually indicated in the testing set, where you have a much higher error rate in the testing set, but in
Mm.
the training set, it's extremely good, like a very low error rate in the training set and a very high error rate in the testing set. That'll be one way uh, to see if your model is overfitting.
Okay. And what do you do if the model is underfitting?
So if the model is underfitting, or
Sorry about that. Like just before that, sorry. um, so how would you fix overfitting in general? Like so with decision trees, we have this max depth that we use, right? But
Mhm.
do you know any general concepts that we might use for any model? Like what's the general concept behind like techniques that you use to reduce overfitting?
Yeah. So there's a lot of methods in terms of uh, reducing overfitting in your model. One of the ways you can do is take a look at your features, right? If you have features that aren't really providing you with information relative to your target, they could introduce spurious relationships and noise that you don't want your model to capture, which will then make it overfit. So that is called uh, feature engineering, right? We reworking your features so that they are the best, as informative as possible. Um, so that is one way you can help with overfitting. Um, like I just mentioned before, tuning hyperparameters so that your model doesn't go as complex as you want it to go can help with overfitting. Um, we also have other techniques. There are also models themselves called principal component analysis that can help you with dimensionality reduction um, as well. And when you reduce your dimensions, right, you're eliminating noise that can throw off your model, and focusing on the central features of your model. So yeah, dimensionality reduction, which kind of coincides with feature engineering as well. Um, any other techniques that I can do? Um, let me see. Yeah, other than hyperparameter tuning, dimensionality reduction.
And features. So what about the model itself? Like I know you said hyperparameter tuning,
Yeah.
but like what kinds of hyperparameters would we tune? Like, uh, yeah, so if you were to think about the model in general, what would cause a model to overfit? And this is similar to what you said with the decision tree, max depth, right?
Yeah.
So, um, like if you were to tune max depth, for example, for different problems, right?
Mhm.
In some cases, you might see that, you know, uh, with max depth of 7, it starts overfitting, right? But with
Yeah.
others, you might see that you actually need, it doesn't perform as well. It probably underfits with max depth 7. So what's going on there?
Yeah. So it all comes down to the data set and the problem you're working with. If it constitutes a higher max depth because your model needs to be more complex, then you're gonna get better performance with a more complex model on a more complex problem.
Oh,
So yeah, it just depends on the problem you have. You know.
right.
Um,
So model complexity, right? That's what you're saying. So you want to increase model complexity if it's overfit, if it's underfitting,
mhm.
and decrease it. So if it were to, like, are you familiar with neural networks by any chance?
Oh, sorry, can you repeat that?
Are you familiar with neural networks?
Yeah, a little bit. Yep.
All right. So if you have deep neural networks, right?
Hmm.
So firstly, can you just briefly describe like what's the architecture of like a deep neural network model?
Yeah, so a neural network, right? The components of it really is you have your input layer, right? Which is going to be, the input you would put to a normal machine learning algorithm, like the features of your data set, right? And then between the input layer and the output layer, oh, sorry, the output layer would be what you want when you're like the target of your model, what you want it to output. So in between the input and output layer, you have these layers called hidden layers, and essentially they transform the data. Um, they're through learned parameters of training, they're transformers. They transform the data at each step through the layers all the way down and funnels it into the output. So you can think of each layer in the hidden layers of a neural network as a transformation function. Uh,
So what's the analog of max depth here?
what's the what? Sorry.
Like max depth is for decision trees.
Yeah.
What's a similar property for neural networks?
Yeah. So no, that can be for your hidden layers, like the number of neurons you assign to the layers. Um,
So
or parameters.
the number of layers itself, right?
Yeah.
Okay.
Minimum.
So how do you choose the right number of layers?
Yeah. So number one, you need to take a look at what kind of problem you're dealing with. If it's a complex problem that is not really um, it's nonlinear. It's you're gonna require more layers with that. Um, Let me think here.
Like just empirically, like how would you go about the process, right? Because yeah, definitely you would start with some number of layers,
Hmm.
and then what would you do? Like you would run the test, then what
Oh,
would it,
I see
yeah,
you want me to say.
how's the process go of
Yeah,
like
so
doing?
I would start with an educated guess of the amount of layers I would need for my problem. I
Right.
would run through the test. I would run it against my test data, see my accuracy or whatever my um, your metric is for your testing. Um, and I'll see its performance based on the training set as well, the performance on the training set, and see whether if it's underfitting, then I need to add more layers. If it's overfitting, then I need to reduce the amount of layers
Makes sense.
from the neural network.
All right. How are these neural networks trained?
Yeah, so um, initially, all the parameters are set to some random numbers, and you pass through your input data through the neural network, and it propagates through, right? You get your result at the end, and then you use an algorithm called backpropagation that essentially it finds the step in which it needs to adjust the parameter so that the target at the end will be closer to the true target, and use that for each parameter using backpropagation.
What do you backpropagate?
I would backpropagate, you said?
Yeah, what do you backpropagate? Like,
Yeah, so
so you did the forward pass, you got an answer,
yeah.
label. What next?
Okay, yeah, then you go backwards, right? Hence the name. And you need to calculate the gradients for
The
the
gradient of
param-
what?
the gradient of the parameter, or the partial derivative of the parameter, with respect to your cost function, right? Your error function.
Your loss function, right? So, and it's the other way around. You find the gradient of the loss function
Yep.
with respect to the parameter. So
hmm
what is the loss function?
Loss function is going to essentially tell you how off your predictions are off from the target. That's what a typical loss function would tell you. So an example would be like mean squared error, which is just the squared difference of your target and your prediction.
Right? When would you use mean squared error and when would you use something else as a loss function?
Yeah. So let me think here. So you have different loss functions for different types of problems. Like you have mean squared error, and then you have cross entropy loss, which are both for different types of problems. And but another reason is some of the loss functions have built-in regularization, which would help also with overfitting.
Mm-hmm.
Um, so that's also one reason why you might choose one over the other. Also, some of them are more interpretable than others. Like you have root mean squared error and you have mean squared error. Mean squared error, you can't just look directly at the value and say, oh, okay, so this value is in scale with my data. If you want it to be interpretable, and just look at the error and be like, oh, okay, that's exactly off by like three wind shares. Your target was wind shares. Um, you would use root mean squared error because then it's scaled back down to your data.
If you had a
So
binary classification problem, which loss function would you use?
if I had sorry,
A
can you repeat
binary classification.
a binary classification problem? What would I use?
Yeah.
Yeah, so you can just use the cross entropy loss. You can use that binary cross entropy loss. Um,
And if you had a regression problem,
a regression problem, you can use mean squared error if you want.
right? So
You can use
that's
that, or
the main difference, right? For regression, you would use something like mean squared error, using the same argument that you said, because you care about the magnitude of the difference.
hmm
For binary, you only care about like, oh, one said zero, the other said one is the zero. So do you know the formula for the binary cross entropy loss?
not at the top of my head. Mm-mm.
Yeah, so basically it's very simple. It's like minus p log p, right? Sum of, so like your binary classification algorithm gives you a probability. So you do like p log p if it's a positive example. If it's a negative example, you calculate 1 minus p log 1 minus p, right?
Okay.
So because like the general form is just a sum, right? You just add up because it's for classification in general. If it's binary classification, you only have one probability and like two terms here. And then one of these terms becomes zero if the if it's a positive example, the so if it's a positive example, this term would become zero, and if it's a negative example, then this term would become zero, right?
Hmm.
So technically, like y into p log p, right? So yeah, that's the formula, and then you'll see that if it's a positive example and your probability is low, because you're always predicting probability of positive. So if your probability is low, the loss is lower. Sorry, loss is higher.
Hmm.
Whereas if it's a positive example and the probability is higher, then the loss is lower. So yeah, you can work that out, but uh, that's the kind of formula. And do you know any regularization terms that you would add to the loss function?
Yeah, so um, you can add a regulation term called L1, which essentially is just the absolute distance between. Oh, sorry, that's just the sum of your parameters um, as a regularization term
Okay.
that would be added onto your loss.
Right. And so what's the idea behind that? Why would you add the weights, this L1 of the weights to the loss?
Yeah, so what that does essentially is it constrains your model to keep your weights as small as possible so you can achieve a small loss. Because if your parameters are large and you're summing that up, you're going to get a very large loss. So it it forces
Forcing,
your model to keep them
yeah,
close to like relatively zero.
makes sense. All right. Have you heard the term gradient descent?
Yes,
What is it?
it is an optimization algorithm that is used to uh, update the parameters in a way that reduces the cost function or your error function.
Right. And do you know the concept behind it?
Yeah, so what we're doing is we're taking the derivative, right? Here, there's gonna be multiple dimensions. So we end up taking the partial derivative with respect to each dimension, with respect to the cost function. And
Hmm.
we're essentially calculating the step in which we need to adjust the parameters so that they are going to reach the optimum minimum of the cost function, right?
Right.
Or when the partial derivative is equal to zero
Yeah.
for that specific parameter.
All right. And how do we decide which direction to take the step in?
Yeah, so we're gonna be negating our step here, so then we can go down towards the optimum minimum. Otherwise, we'd be going up.
Right. And
So
then we could go in multiple directions. How do we choose a direction?
um, so yeah, the direction is gonna be towards the optimum minimum. Um, so we essentially set it equal to zero because that's our goal is to so that the derivative of that parameter is equal to zero. And then we look at that step that would make it closer to zero.
Right. So we choose the direction that reduces the loss function the most.
Yeah.
Yeah. So we find the gradient of the loss function and we choose the direction with the highest gradient, right?
Hmm.
And what about the step? How do we know how much of a step to take?
Yeah. So that is actually determined by your a parameter called a hyperparameter called alpha or
Right.
learning rate.
Yeah. As you're training a model, how does the alpha change across time? Like, you
Oh,
have one alpha that you use throughout your entire training run, or
yeah.
are there sophisticated ways of choosing alpha?
Yeah. So your alpha, your learning rate is basically how big of a step you're making towards uh, you know um, achieving the optimal parameters.
Hmm.
So usually people have it a constant where it stays the same. The step is always the same size. but you could actually adjust it with our learning schedule, and it actually dynamically updates during your grading descent.
And
Um,
how would you choose it? Like, what would be a reason? Like, any idea on what kind of schedule you could choose?
yeah, so a common learning rate is about 0.1 because it's not it's a balance between taking too big of a step um, and taking too little of a step. So 0.1 is a harmonic kind of type of value that a lot of people use to start off with. Um, but if you
Right.
notice, oh, sorry.
Like as a schedule, right? So maybe you could have a higher learning rate in the first epoch or like, initial runs and then
Hmm.
gradually reduce it, right? Because
Yeah.
when you initialize a model from random, so initially you want to take like big steps because everything is very random.
Hmm.
But after you've taken a bunch of these big steps, you probably converge to something more reasonable already. So you don't want to lose that. You don't want to go off in a random direction again. So over time, then you sort of reduce the learning rate, and then that helps it converge, right? Otherwise, it could just go into a different space altogether. Like there's a risk that it could just like miss the minimum, go off in a different direction,
Hmm.
right? So if you come to the whiteboard for a second, uh,
Total whiteboard. Okay.
uh,
Yeah.
so if this is like your gradient surface, right?
Hmm.
And then let's say you're here, right? And then let's say you took like a big step. So you might miss this and you might just go like, you might just end up here because you took too big a step, right?
Hmm. Yeah.
So if you keep doing that, you'll just keep oscillating like this. So when you're here somewhere, when you're here somewhere, you want to take like big steps towards the minimum because those big steps will get you closer and closer. But when you're here, you want actually to take smaller steps, right? So, and how do you know you're here? Because just by saying, I've seen more of the data, so I'm probably in a reasonable space, right? So
Hmm.
I'll now take smaller steps. All right. What else is there? Okay, just one sort of more practical question. Let's say you're Amazon and you're designing the front page, which has a list of products, right?
Hmm.
So user opens a page, they see a list of products, and now obviously for this user, we know their buying history, and we have all the data about the interactions at Amazon, and we have all the data about all the products used in Amazon as well. How would
Hmm.
you model this as a ML problem?
Yeah. So what you said was you have an Amazon front page, and your goal is to uh, use an ML model to suggest the most recommended products based on their buying history.
Yes.
Yeah. So with this type of problem, clustering really shines here. You can use an unsupervised algorithm like clustering uh, to find similar products to uh, what the consumer has bought. And
But what if
yeah,
you want to do it, you want to model it as a supervised learning? Because, the problem with clustering is it's really not that complex. So if you go back to the underfitting, overfitting discussion, clustering models will almost certainly underfit, especially a problem like this, which is very difficult.
hmm
The clustering just doesn't have the generalizability or the power to represent the actual relationships between users and items at that scale. I mean, you'll get some reasonable results, don't get me wrong, but firstly, like clustering won't be personalized in a way because any user who's purchased a product, like will sort of fall in a similar category, right? It's not really personalized, is what I'm saying, right? It's not really tuned to like you as a person, uh, because it's just like you are similar to like a bunch of other users who all have like very similar buying history. And then the other thing is like I've bought like 100 things in the past. How do you combine, like each one of those belongs to maybe different clusters? How do you use that to generate recommendations? So let's try to model it as a supervised learning approach. How would we do that?
Hmm. Let me think here. Um, so don't know if this is viable, but um, you can use a linear regression um, to predict the probability they would like the specific product. Um,
Okay.
or better yet, instead of linear regression, we use logistic regression because that's what it's, if we're doing a probability, we want to use logistic regression. Um, but and the way we can create a model like that is, so we need to represent these products as a vector, a collection of values. So we need to take like the main points of information from each product and standardize it into a vector. And that way we can feed into a model, and then they can train, learn the parameters that are specific to the buyer, and then output a probability. But that isn't really scalable if you have a large consumer base and you have to train a model for each consumer. Um, but that is also another way you can do it with supervised.
All right. And how would the training data look for that logistic regression model? What is like one row in the training data?
So for your input or your X, it's going to be your features of the product. So maybe you want to, one of the features will be a multi-class one, like if it's uh, used for sports or entertainments. But basically, the features described in the product as that could be applicable to all products on the Amazon website. Um, that'll be a vector there. And then for your output, it's just going to be one representing that, okay, the consumer bought this product. And then zero would mean the consumer did not buy the product.
Right. But then is it not just the product features that are in there, but also the user features, right? So the input is a user and product pair, isn't it? And then the output is a probability.
Hmm.
So you want some way to represent the user as well, right? Because like you do this for all the users and all the products, all the possibilities of users and products. That's your data set.
Yeah, I see what you mean. Okay. Yeah.
Right. All right,
Mhm.
we can end the interview here. So before I share my feedback, I want to understand from you how this interview went. What are the things you did well, and what are the areas for improvement?
Yeah, so for me, I definitely can point out I have a lack of knowledge in machine learning. I can definitely brush up on a lot of the fundamentals, the algorithms, a little bit about why you would use one algorithm or the other. Um, so, I need to work on my fundamentals. Also, I need to slow it down a bit. Sometimes I like to jump in and just answer the question without a kind of path my mind of what I want to say exactly. I should slow down, try to mentally structure what I'm going to say before saying it, so it comes out clear and understandable to the interviewer. So yeah, those two right now I can think of. Um, as a strength, I think that when the words do come out, I can communicate loudly and somewhat clear. Um, it's a little bit of communication, though it could work. I think that communication is a little more my strong suit. Um, and that's at the moment that's all I can think of right now for advantages.
Yeah. So overall, you actually did pretty well. This has been like I've been interviewing a lot of the people from AI for all, and I'll be honest, like this is one of the better interviews that I've conducted. In just in terms of like, I think you did a good job with most of the concepts. Um, and then, yeah, I think in terms of areas for improvement, uh, I think maybe on the practical aspect is where I would say your biggest gap is. I think on theory you're doing pretty well, right? So, yeah, one thing on the theory, maybe you're missing a bit of depth there, which you would have realized through this interview as well, like cross entropy loss. Binary cross entropy loss is you know pretty simple formula. It's used for almost every binary classification, so it's worth knowing that, right?
Hmm.
It's also worth knowing regularization. When I asked about overfitting, you didn't mention regularization, but when we are talking about loss functions, you did mention it. And then just being able to simply say that regression problems would use mean squared error and classification would use cross entropy. I think that's like a pretty fundamental thing which almost everyone who works in ML knows, right?
Okay.
So I think those were two or three things that was sort of missing. And then on the practical aspect, like, yeah, just how do you model a problem as an ML problem, right?
Hmm.
Um, so I think for you, where I would focus more on is actually not too much on theory per se. I would actually encourage you to try running machine learning training in practice, right? So
Hmm.
like actually training these models and getting a sort of more practical experience. So there are websites like Kaggle where you can try out various challenges that they post from time to time. Or you don't even have to do that. You can just train some models on your own machine. Just see that underfitting, overfitting thing happening in practice. Actually work with constructing training data that you feed into the model yourself, right? That helps you understand like what are the challenges with the training data. Like if you don't get your training data right, what happens? Uh, and then feature engineering. So I did mention some good feature engineering techniques, but uh, you know, like being able to implement them in practice is a very valuable skill. But
Hmm.
overall, I said you did pretty well. I would say it's borderline. Like I wouldn't necessarily hire you if you were interviewing right now. But given that you're still in like university and still learning, it's pretty good, right? It's one of the better performances I've seen. So I'm pretty confident that if you continue down the road that you are on, continue learning, continue practicing, you have a really good chance to actually become an ML engineer when you graduate. So yeah, good luck and yeah, congrats.
Yeah, yeah. Thank you for coming out today and doing this with me. Yeah, that was my first ever like I've done like software engineering interviews, but I never done like a machine learning one before. So that was definitely an eye opener. Um, so yeah, I
Yeah.
really appreciate you coming out and helping me with this. So
All right. I'm happy to answer any questions you have.
yeah, so I'm actually like um, though I did this interview today for machine learning, I'm actually striving to become a data scientist. Um, so I know that machine learning is more as a tool in that type of field. Um, but it's still, you still think it's just as important to achieve this level of like to go as deep as I can with machine learning in terms of
Learning is like a really good skill to have as a data scientist or as an ML engineer. I would say that ML engineer is probably better in terms of your career opportunities. Not that data scientist is anything to sneeze at, but like you just get paid more, I guess, as an ML engineer, and you have more opportunities to advance. I would say, especially in like big tech companies, like FAANG companies. But given that your background is more on statistics, data scientist is also like a solid choice. So the main difference I would say is that ML engineers uh, have better coding skills, so they know, like, they're more familiar, like, they're better at coding is what I would say. Like, they just can write like better Python code. Um, so yeah, like if you're good at coding, then I would actually encourage you to go down the engineering path. And I think that's ML engineering is like a really good role where you need like deep statistics knowledge as well as coding knowledge, and then it is like one of the most prestigious and most high paying jobs that you can get out there, and also sets you up well for the future.
hmm Yeah.
But at the same time, I won't force it. Like, if you don't enjoy coding as much and you're more deep into statistics, data scientist is also like a very solid choice. But like
hmm
you said, with data scientist, you need like the core stats knowledge much more than you need like the ML knowledge.
hmm Yeah.
All right? Any
Okay.
more questions?
Um, let's see. Let me think here. I had a question in mind, but it's isn't coming straight to mind. Hmm.
Think about it. It's okay.
Yeah. Let me just think, because I want to make sure I answered all I want to answer. Um, let me think here. So for a position like an ML engineer,
hmm
um, oh, and like in interviewing for ML engineers, how large of a portion do you think like the neural networks would be for for the interview? How large, how big of a part of the interview would be just dedicated to neural network knowledge? Um,
Not a huge lot. I think conceptually, like the concepts that you already know, based on like your knowledge from this interview, I think in terms of the pure concepts, you would actually stand a good chance. The main gaps I would see is mainly around like the practical aspects, which is like things like, you know, I want to do like product recommendation for Amazon. How do I model that as an ML problem, right?
hmm
And just being like, any ML engineer will just say in like a couple of seconds that, oh, first thing you do is user product predict probability, right? And then go into like, okay, what are the user features? What are the product features? Whether you use logistic regression or neural network doesn't matter in the scheme of things, because more or less it's a black box. But you do need to be able to understand concepts like overfitting, and then saying like, if it's neural network, I add more layers that might cause more overfitting, things like that.
hmm
So it's more about like, how do you translate a business problem into an ML problem correctly, and then how do you construct the training data? How do you construct the features, right? And then
hmm
reasonable choices on models, like, obviously you won't use clustering, for example, right? You would use random forests or neural networks, or GBDTs, or even logistic regression is like a good choice for to start with. And then it's about, how do you evaluate the model, right? If something goes wrong, how do you know? How do you figure? figure out like what went wrong and how do you fix that. And those are more the practical aspects. And the way you learn that is just by doing it yourself, right? Just by like training models yourself and trying out different things and seeing what happens, you
Hmm.
know. So it's learning by doing is the main thing I would focus on for you, right? Like if you're able to do that in the next year or so, that sets you up really well with the theoretical knowledge that you already have.
Okay. Mm.
All right. If that's yeah. Any do you have any other questions?
No, that's all my questions.
All right. Cool. All right. Best of luck with your preparation and your studies, and hope you do well in the future. And have a nice day.
Yep. You too. Thank you.
Yeah.